So now that we've talked a little bit about position versus time graphs, we're going to now use a position versus time graph to create a velocity versus time graph. But first I want to review what we know so far. So far we know that the y-intercept on a position versus time graph, be it here or here, whatever it is, that is going to be the starting position. So at time 0, you're going to go up and just look at how high the line is. So in this case, the starting position is 0 because it is at a height of 0. And the slope of a position versus time graph, if you think about it, okay, how far did I go is how far you go up, and how much time that took is how much you go over. That is the slope. So the slope here is my velocity. Next, if we want to know the actual height at a location, let's say at 3 seconds, I want to know what's going on. Well, I go up here and it's at a position of 3 meters. So when we're thinking about the height on a position versus time graph, that is the location, or what we call in physics the position. And lastly, if we're looking at the change in height of the graph, that would be like, okay, well, at the beginning, it's at a height of 0 right here, and at the end, it's at a height of 4. This change in height is my displacement. So displacement is how far it moved. So just looking at where it started compared to where it ended. All right, so now what we're going to do is we're going to create a velocity versus time graph. And if you remember, our velocity is just the slope. Now, I want to make sure that we're focusing on the fact that this is a position versus time graph. This only works on a position versus time graph. So the slope of a position versus time graph is my velocity. And you'll notice here that this part of the slope between 0 and 1 second, the slope is 1. Well, that means that my velocity would be 1 between 0 and 1 seconds. And then between 1 and 2 seconds, the slope is still 1 because it goes up 1 over 1. And between 2 and 3 seconds, the slope is still 1. And between 3 and 4 seconds, it's still 1. So I'm going to end up with a horizontal line for my velocity versus time graph at a height of 1 meter per second. Now, don't get confused. This does not mean it starts at a position of 1. This is just the velocity. So the example I like to give is if you were driving and you lost track of where you were, you don't know where you are, you don't have GPS, you call up your mom on the phone and go, "Mom, I'm lost. I'm driving 1 meter per second and I don't know where I am," and she's not going to be able to help you. So the velocity versus time graph is as if you're looking just at the speedometer of your car. You don't have any idea where you are unless you're given the information about where you started. But from the velocity versus time graphs, you have no idea where you started. All right, so let's take a look at the next one. Number 4, again, we're not worrying about where it starts to find the velocity. We only care about the slope because the slope is our velocity. All right, so this slope here, if we go over 2 and up 2, that's still a slope of 1. So remember that it's rise over run. So for between 0 and 2 seconds, that slope is 1. And then this part, we just have to be careful because this goes down 2 and over 1. Well, rise then is -2 and run is +1 because I'm going to the right. I'm going from 2 to 3. So rise over run is going to be -2 over 1, which is -2. So that means that this is going to have to drop down to -2 here, because that slope stays the same all the way from 2 to 4 seconds. Now in math class, they're very specific about when there's dotted lines and when there's solid lines. In physics, we really don't care as long as it's obvious what's going on. Now, I like doing a dotted line. If you want to do a solid line, I don't care. I don't like leaving that gap though, because this shows me, okay, all of a sudden it goes from a positive velocity of 1 to a negative velocity of 2, and I have that dotted line to connect them. If you ever end up with a 0 velocity, make sure that you're drawing it really fat on the horizontal line. If I don't see your pencil or pen mark, I'm not giving you credit. So you have to make sure that you're showing that. And last but not least, we have this nice one here. We're going up 2 over 1. So this is a slope of 2. So that means my velocity is 2 between 0 and 1 second. And then this part is up 1 over 2. So up 1 over 2 is going to be a slope of 1/2. So that's going to be right here. And again, I'm going to connect those two lines with a dotted line. So let's think about our velocity versus time graphs now. For many graphs, both the slope of the line and the area between the line and the horizontal have physical meanings. So the slope of a position versus time graph tells you the velocity. We've been using that to figure out my velocity versus time graph. But looking at the velocity versus time graph, I need to think about what the area means. So the area on number 3, if I go back to number 3, and if I want to know the area, I'm going to be looking at this. And it asks me for the units of the area. Well, when I'm looking at this, the height of this is 1 meters per second. And the width of this is 4 seconds. Well, if you remember to find the area of a rectangle, so to do the area of a rectangle is length times width. I'm going to have the 4 seconds. So I'm just going to put seconds here times my width, which is 1 meters per second. And a lot of times students will think, oh, that's going to be meters per second squared. But if you notice, this is going to be seconds over 1 times meters per second. And so when I multiply these, I'm going to multiply them across. So I'm going to have seconds times meters divided by 1 times seconds. And when I do this, the seconds cancel out. And so the units are going to be just meters. Well, meters measures distance. So that means that the area between 0, so we're not going to go all the way to the bottom of the graph. We're going to go from my 0 to the line of the graph. This area is my displacement, which is kind of cool. Now, be careful, because what we just talked about up here is the change in height of the graph is displacement on a position versus time graph. But when we're doing a velocity versus time graph, the area is going to be our displacement. So you're going to start seeing some different shapes of velocity versus time graphs. And depending on those different shapes, you are going to be able to find the area from 0 or from the horizontal axis to the line of the graph, either be it up or down, and that will tell you how far it went. Now, a couple of things to think about is that when you have a velocity versus time graph that is a triangle, well, the area for a triangle is 1/2 times base times height. You might have the area for a rectangle because it's a constant velocity. This area is just base times height. Or you could have a trapezoid. And if you have a trapezoid on a velocity versus time graph, let's say you could have a trapezoid like this, you can just add this rectangle plus the triangle together, and it makes your life a lot easier. Or perhaps you might have something like this where you have an object that starts where it's already moving and it speeds up, and you need to know how far it goes. Well, then I can chop this into a triangle and a rectangle this way. So here I would have my rectangle, and here I would have my triangle. So just remembering all of those different things, and that'll help you out. Let me know if you've got questions.